Versions of a spectral theorem. We have a complex spectral theorem, which says that if V is a complex inner product space, F is a linear operator on V, then F is normal if and only if V has an orthonormal basis consisting of eigenvectors of F. And then we had the real spectral theorem, and the real spectral theorem says for V a real inner product space and F a linear operator, F is not normal but self-adjoint, which is stronger than normal if and only if V has an orthonormal basis consisting of eigenvectors of F. Okay, so remember that self-adjoint means F equals F adjoint, and normal. We have two characterizations. Our definition was that F commutes with its adjoint, and that was equivalent to, for all V, the norm of FV is the norm of F star V. So combining these two theorems, well, and restricting to a special case at the same time, we can make the following observation, combining it with one of our older characterizations of what it means to have a basis of eigenvectors to be diagonal. Suppose that F is self-adjoint. So I'm not using the full power of the complex spectral theorem, but just assuming that F is self-adjoint and therefore normal. And let lambda 1 up to lambda m be distinct eigenvalues. For F, then V is the direct sum from j equals 1 up to m of the null of F minus lambda j I'd V. So that we know, because this is equivalent condition to having a diagonal, a basis that makes it diagonal, but it's special. This is not just any basis, but an orthonormal basis. So we can also say that each vector in each space null F minus lambda j I'd V is orthogonal, because this is an orthonormal basis to the other subspaces. The last time we saw this, we didn't have an inner product, so we couldn't talk about that. And it wasn't necessarily true. Okay. And the proof of that is just combining these spectral theorems with the old theorem of equivalence of conditions for F having an orthonormal basis. Okay, so we've covered now a real situation and a complex inner product spaces. And the operators we're looking at might be self-adjoint, and they might be normal. The real spectral theorem said that if I have something which is self-adjoint, a self-adjoint operator in a real inner product space, there exists an orthonormal basis of eigenvectors of F. That if I have a complex a normal operator in a complex vector space, there exists an orthonormal basis of eigenvectors of F. And since every normal operator is also self-adjoint, we know also here there exists an orthonormal basis of eigenvectors of F. And what we haven't said anything about yet is that square there? What happens if we have a normal operator on a real vector space? Can we say anything? And so today we'll talk about what we can say in that situation. It's a little bit more complicated. So as you probably suggest, that would have been part of the real spectral theorem if the answer was I get a diagonal matrix. Right? So the answer is not that I get a diagonal matrix. So not that there exists an orthonormal basis of eigenvectors of f making this thing diagonal. And the general kind of failure of having an eigenvector in the case of a real vector space, when we fail to have an eigenvector, we still get one of these invariant two-dimensional subspaces, right? Like a rotation. Which is of course connected to the fact that we can't, we don't have the fundamental theorem of algebra. We can't find roots for all of our polynomials, but we can at least factor our polynomial into linear and quadratic factors. And so we have to figure out how that failure to be diagonal or failure to factor affects our spectral theorem, and that will give us the answer of what appears in this square. So that thinking suggests that the first thing we should look at is a two-dimensional real inner product space. Right? That would be enough for this degeneracy to happen. And we should look at an operator which is normal but not self-adjoint. And see what we can figure out about that operator. And that will give us a clue as to how to fill this in. And then we just need to extend that to higher dimensions. So that's the reason for the following lemma, which performs that analysis. Suppose V is a two-dimensional real inner product space and F is an operator on V, then the following are equivalent. First of all, this condition, right? We want to look at exactly this square. So we want to look at F being normal but not self-adjoint. And we want to figure out what that means. One characterization of what that means is that the matrix of F, and I should say there's a basis, right? So the matrix of F is of the form A minus B, B, A. Which is a very particular form. It only has 2 parameters instead of 4. And that's true for any orthonormal basis B. So no matter what orthonormal basis I choose, I get something of the form A minus B, B, A. Of course, the A and the B change, but they always have that pattern. C, and if you remember when I gave an example of something which was normal but not self-adjoint, that was what the example looked like, and that was no coincidence. And C, there exists an orthonormal basis B such that the matrix with respect to that basis F is of course like this, A minus B, B, A. I'm sorry, in this one, B should be non-zero. Because if B was 0, this would be self-adjoint. It would be symmetric. Okay. So with B non-zero, and the third one, B is positive, strictly positive. Okay. If B was 0, this would just be A, 0, 0, A, and it would be self-adjoint. And so it wouldn't be true that it's normal, but not self-adjoint. Okay, so let's prove this. So we'll start with A. Suppose A holds. And take B to be our orthonormal basis. And we want to consider the matrix. So I just know B is an orthonormal basis. I plug in my F, I get out a matrix. At this point, I know nothing about the matrix. So I'm just going to put in A, B, C, D. Just four variables. And we want to prove that it has that form. So if we look at the first column is E1, E2, E1, E2. The first column, A is the coefficient of f of E1 for E1, and B is the coefficient of f of E1 for E2. So the norm of f of E1 squared is A squared plus B squared. I don't need to take absolute values because these are real numbers, and when I square a real number, I get back a non-negative number. In the first column, I can get by saying, the first row, I can get by taking the conjugate transpose. I have an orthonormal basis. And looking at the adjoint, f star of E1, that's equal to A squared plus C squared. Right? But this is normal. For a normal operator, the norm of f of v equals the norm of f of star of v. And so these two things must be equal. If these are equal, that means that b squared equals c squared. Now for real numbers, there's two things that can happen. Either b is equal to c, or b is equal to negative c. We can't have b equals c. If we had b equals c, it would be the same type of degeneracy that would make this matrix symmetric and therefore self-adjoint. So we're saying that f is normal, but not self-adjoint. So b equals c is out because we know the matrix is not self-adjoint. So it must be that b equals negative c. So that means so far we've worked out some restraints, some constraints on the matrix with respect to this orthonormal basis, which was arbitrary. That is, we know now that the matrix with respect to any orthonormal basis of f is of the form A, B, minus B, D. And what's left to show is that A and D are actually equal. So we've used one of the two characterizations of what it means to be normal, which is that f and f adjoint applied to a vector result in the same norm. The other characterization we have of normality is that f and f adjoint commute with each other. So you can use that to get another restriction because it implies, after taking the linear transformation matrix with respect to basis B, that the matrices will also commute. That is, we have that MB of f, MB of f star has to equal MB of f star, MB of f. We know MB of f, that's A minus B, B, D. MB of f star, if you remember, is equal to the conjugate transpose because we have an orthonormal basis, so that's AB minus BD, and that equals the same thing but in the other order, A minus B BD. If you multiply those out, well, there's something here, something here, something here that we don't necessarily need to worry about. In this entry, I get AB minus BD And on this side, similarly in the top right entry, I get BD minus AB. So that means each of these we could factor, so that means B, A minus D equals B times D minus A. So we have a real number which is equal to its negative, and therefore it's 0. If it's 0, either B is 0, but we can't have that because then this matrix will become self-adjoint. So it must be that B is not 0 and A minus D is 0, so A is equal to D. And that proves that in the lemma, the first part A implies the second part B. Okay, so let's continue. So to continue, let's suppose that B holds. We want to show that C holds. Let B be our orthonormal basis. And we want to show simply, we've got already something of the right form, and we want to show that we can choose B to be, choose the basis so that B is positive. Well, okay, we've chosen a basis, we write the matrix, we know it has this form by what we just showed. So if B is already positive, we're done. If B is negative, instead we use E1 minus E2. And that will flip the sign for B. So B implies C. And finally, if we suppose C, again we know B is not 0 because it's not self-adjoint. And you can multiply, but we want to show that it's normal. So it's not self-adjoint. But we can show that it's normal by showing that f star equals f star f. So we just multiply these out and show that these two matrices are in fact equal. MBF, MB, f star equals MBF star, MBF. Okay, so we're trying to analyze this missing case where F is an operator on a real inner product space. It's normal, but it's not self-adjoint. Now we understand something about what happens for the two-dimensional invariant subspaces. Two-dimensional subspaces. We also, from earlier theory, know something about what happens with one-dimensional subspaces. And so what we're going to do is create an induction where we peel off the subspaces to produce a matrix which is going to be block diagonal, having either 2 by 2 or 1 by 1 blocks. But in order to perform that kind of peeling off, we have to show that at each stage when we take off a subspace and we leave its perpendicular, its orthogonal complement, we take off a subspace U, we leave U perp, we have to show that what's left over is an invariant space. So that's this proposition. If you remember, in a previous proof, we had something very similar, but we weren't able to show that it was invariant, and we had to adjust our eigenvectors and adjust it in order to get to the answer. Okay, so suppose F is a linear operator on V, which is normal. V is a real inner product space. U in V is an F invariant subspace. And I should say V is a real product space. That's what we're looking at. So this doesn't actually need to be real. Let's just say an inner product space. Then, first of all, the orthogonal complement of U is invariant under F. So that's kind of what we need, right? That whatever is left over after I peel off one of these 1 or 2 dimensional subspace is invariant under F. Secondly, U is invariant under F adjoint. Taking the restriction to U and then the adjoint is the same as taking the adjoint and then restricting to U. The restriction of F to U is normal. And finally, the restriction to U perp is normal. And so this will enable us to do this subspace removal procedure in order to use the two-dimensional case to cover all cases. Okay, so proof. Let's take an orthonormal basis, E1 up to EM of the subspace U, and extend it with G1 up to Gn to an orthonormal basis of V, and call this combined basis E1 up to Gn, the basis B. Now if I write F in this basis, its matrix, the top is going to be labeled by E1 up to En, followed by Em, followed by G1 up to Gn, as are the columns. So we should think about this matrix as being partitioned into 4 blocks. U is F invariant, so it sends something in the span of E1 up to Em into something in the span of E1 up to Em by some matrix A. And it never has any coefficients outside of that because it's invariant. The other situation, if I start in something in the complement, I don't yet have any guarantee, right? It can have coefficients that are both in U, in the basis for U, and in the basis for U complement. And what we want to show that U perp is invariant under F, is that this B here is 0. That submatrix is actually just the 0 matrix. And just as with the spectral theorem, the way we want to do that is to examine the norms, see how those correspond to rows and columns, use the fact that the thing is normal to show that they're equal, and this, therefore, the extra stuff has to be 0. So, efficient way to say that is that for all j, the norm of Fej squared is equal to the norm of F star Ej squared by normality, which is equal to the sum j equals 1 up to m norm of F Ej squared. So, I should say, the sum from j equals 1 up to m norm of F star Ej squared. And so on this side, we have a sum of squares of absolute values of entries of A. And on this side, we have the sum of squares of absolute values of entries of both A and B. And since they're equal, and where it's a sum of non-negative things, it must be that. So B is 0, and U perp is F invariant. the first one on the list. That's really the thing we had to do a little work for. The rest of them, you just think about it a little bit. Basically, so B, take the conjugate transpose. And so since B is 0, the thing in that spot will be 0 after taking the conjugate transpose. C, if I take any V in U, U in U, inner product of F restricted to U, U and V is equal to F of VV by invariance is equal to U F star of V. And this is something in U, and that's equal to U F restricted, F star restricted to U of V. And so that just says that this thing F star restricted to U solves the adjoint equation. That is, it's a thing to plug in here to make these two inner products equal. So it must be equal to the adjoint, whatever it is, of F restricted to U. And D, we observe that F commutes with F star and F restricted to U star equals F star U, and E can be obtained similarly. So really it's the first one, the other ones are just simple corollaries. Okay, so this brings us to our theorem. Sorry, so F, so you use the fact that, this is sort of a, use the fact that F star equals F star F, and that fact. Theorem. Suppose F is a linear operator on a real inner product space. So this is sort of an extension of the spectral theorem for the reals, or for the complex. F is normal if and only if there exists an orthonormal basis of V such that the matrix with respect to this B of our F is block diagonal with blocks of either 1 by 1 of the form lambda, with lambda that has to be an eigenvalue, or they're 2 by 2 of the form A minus B, B, A. And B is greater than 0. Okay, so prove this. So suppose, and we just are going to peel things off for the harder direction. So suppose first that B is an orthonormal basis, and this block diagonal structure holds then a quick consequence of that is that the matrix in this basis of F commutes with the matrix in this basis of F adjoint. Why is that? Well, diagonal matrices commute. Multiplying two block diagonal matrices means I just multiply all the blocks, then stack the result back into a diagonal. And these 2 by 2 things commute, as we showed in the two-dimensional lemma. That's the easy direction. The harder direction is to suppose first that F is normal. And we want to perform induction on the dimension of V. When the dimension of V is 1, okay, that's immediate. When the dimension of V is 2, we have two cases. If F is self-adjoint, use the real spectral theorem. To obtain an orthonormal basis, if F is normal but not self-adjoint, use the two-dimensional lemma that we proved at the beginning. So now we want to assume that the dimension of V is greater than 2 and that it holds on all smaller all vector spaces of smaller dimension. So by an earlier lemma, or an earlier theorem that we had in the class, we can assume that there's an invariant subspace of dimension 1 or 2. So let U be an F invariant subspace of dimension 1 or 2 if the dimension of U is 1, any non-zero will do as the eigenvector, and then rescale it to give it norm 1. And we're going to add that onto our basis. If the dimension of U is 2, F restricted to U is normal, but not self-adjoint. And so we use our lemma to get that it has a matrix, a block diagonal matrix as desired in some orthonormal basis E1, E2. In both cases, I have an orthonormal basis of either a 1 or 2-dimensional space. And now, to finish the induction, I need to look at U, the orthogonal complement of U. This thing is F invariant by our second result, our second lemma. It's F invariant moreover, the restriction of F to what's left over, F restricted to this space, is normal. So I can use the induction hypothesis. By induction, there exists an orthonormal basis of this subspace, U perp, so that F restricted to that space has the desired form. That is, it's block diagonal with blocks of size 1 or 2, where the size 2 have the form A minus BBA. And then we just adjoin this guaranteed basis for the orthogonal complement of U to our new element, to our new basis, which is either the normalized U or E1, E2. And then we get a basis for the whole space that has the desired property. Okay, so that finishes our sort of extended spectral theorem. The next topic is another special kind of operator and some decompositions of operators into products of more well-behaved operators. So I'll just do the very beginning of this, and we'll continue with it on Monday. And so this first type of operator that we'd like to consider is something called positive operators. So an operator is called positive sometimes called positive semi-definite, which you might have seen used to describe matrices. If it is self-adjoint positive operators are all self-adjoint, and we have one further restriction, which is that the inner product of FV and V is always non-negative. So one thing we can note immediately from that definition is that if V is a complex inner product space, then F, an operator on V, is self-adjoint if and only if FV, V, is in R for all V in V. So that was a corollary we've had already. And so as a result, the inner product of FV and V simply being positive without the self-adjointness condition implies self-adjoint in the complex case, in a complex inner product space. Okay. So the self-adjointness condition here is only needed in the real case. In the complex case, the self-adjointness is already implied by simply requiring that the inner product of V and F of V is non-negative. Some examples. All these orthogonal projections that we looked at earlier. Orthogonal projection is positive. And for the theorem characterizing positive operators, I need to first make a kind of a definition. Suppose F and G are linear operators. We say that G is the or is a square root. Just say a square root of F if, well, the obvious thing, g squared, that is g composed with g, is equal to f, applying g twice. Then some operators can, if they're idempotent, like a projection operator, it's already its own square root by that definition. And then the theorem, characterizing positive operators, I'll just write it up, but I won't give the proof until next time. Theorem. Let F be an operator on an inner product space. Following are equivalent. F is positive. F is self-adjoint. And all eigenvalues of F are non-negative, so in particular real. C, F has a positive square root. D, F has a self-adjoint square root. And finally, there exists some g, some other operator g, such that you can write F as g adjoint times g. So there's our characterization of what it means to be a positive operator. I'll put the proof off until next week.